Hello, dear students. Welcome to the channel and very welcome to this new course that we are starting from today onwards. It is called Instrumentation and Sensors. It is a subject that is being offered in 6th semester civil. It is a program elective course, and in order to get understanding of this course, you need basic knowledge of BEE subject which is being offered in first semester. I am assuming that you all have very basic knowledge of BE subject and commencing this course. Either ways, uh, even if you don't have much idea, I will be giving you hints, pointing out different scenarios and different things from BE subject. So there is no need to worry. We are going to have 2 lectures in a week, sometimes 3, and we will be moving forward with total 4 chapters we have in this course, as you can see here. So the first module which we are going to start today is going to be weighted 25%. It includes the fundamental of measurements and sensing and instruments. So today we are going to start with the definition of measurement and instrumentation, physical variables, common type of sensors. So let's see how far we can go. In this chapter we are going to discuss the different functions of these sensors. We are going to see how we can use appropriate terminologies in order to discuss the sensor applications and qualitative interpret signals from the known sensors. We are going to see how many different type of instruments are there and how you can uh, get best out of them. We are going to see the specifications of both instrumentation and sensors. We are going to see how we can install these instrumentations and how we can where do we place the sensors in order to get the best range of that particular sensors. And we will also see how we can temporarily install your instrument in order to get your work done, get to satisfy your objective only. Second chapter is called sensor installation and operations. We are going to discuss it in the next chapter. Third module is data analysis and interpretation. We are going to discuss that later on. And the fourth one is called frequency domain signal processing and analysis. So first, let's start and discuss the first module, fundamental of measurement, sensing and instrumentation. Let's quickly come back here. This is the book which I am going to use for the demonstration of the subject. It is called Measurement and Instrumentation Principle. The author is Alan Morris. It will be easily available on LibGen, so you can go on Library Genesis and download the book and you can refer it. So let's start. Let me take you to the basic index of it. We are starting with the principle of measurements. We are going to discuss the measurements units. So let's first come here and see what we are going to discuss. Measurement definition and instrumentation we are going to discuss, and physical variables we are going to discuss. So let's go to introduction to measurement. So what is a measurement to you, right? Because we are using measurement in our daily life, in our daily routine for a long time. If you think about it, when you wake up and when you go to the sink and try to brush your teeth, you measure how much toothpaste you want. That is a measurement. That is a customized measurement that you took of a toothpaste. And till then, to the end of the day, when you go to your bed, before that, when you take your dinner, you measure how much do I need to eat. That is also a measurement, isn't it? So measurement techniques have been immense has been of immense importance ever since the start of the human civilization. When measurements were first needed to regulate the transfer of the goods in a barter trade, if you remember the barter trade before the money or the capital trade came into investment, there was a trade called barter trade in which we used to trade different objects for different objects. So it wasn't like just if I want to if I want to buy a chocolate, I wouldn't go to the store and I will simply give money. I will not pay in money, but I will pay in some other term. That was a barter trade before we developed this monetary system. So we used to use barter trade to ensure the exchanges were fair. Industrial revolution during the 19th century brought about a rapid development in the new instrument and measurement techniques to satisfy the needs of industrialized production techniques. And since that time, there has been a large rapid growth in the new industrial technology, and this has been particularly evident during the last part past 20th century, right? When uh, the the method of trading strictly became totally based on exchange of money or capital exchange, right? Earlier, uh, in the time of the Romans or other kings, we used to have the barter trade. So the massive growth in application of computer to industrial process control and monitoring tasks has spawned a parallel growth in the requirement for the instruments to measure. Not only measurement, but in recording the control process variables as well, right? And as a modern production techniques dictate working to tighter and tighter accuracy limits, as an economic forces limiting production cost become more severe, so the requirement for instrument to both accurate and cheap become ever harder to satisfy, which is actually a problem. And it is bigger problem to the people who are working in the industries, who are working on the R&D department, right? Who are developing something new. We who are developing new technologies, who are developing new medicines, who are developing new uh, any new industrial equipment. So for manufacturers, that is a problem. And in past few years, the most cost effective means of improving instrument accuracy has been found in many cases to be inclusion of digital computer power within the instruments themselves, which what do we use? We use sensors, right? And this intelligent instrument therefore feature prominently in current instruments manufacturers catalogs. You will find sensors everywhere. You will find sensors in almost every single digital device that you purchase. You will be having sensor in your smartphone, your smartwatch, your washing machine, your television, your car, right? There is sensor in almost everything these days. And when you have sensors, when you want to measure something, how do you measure it without a unit? It is not possible to measure something without a unit, right? So how do we measure it? We have unit. Now if I ask you what is the unit of distance, you would say, sir, it is meter or kilometer, or if you're British, you would say, sir, it is miles. If you're American, you would say miles, right? uh, if I ask you, how much do you weight, how are you going to say, sir, I weight fourth of a cow that my neighbor holds? No, you can't say that. No. So how do you say it? Sir, I weight 50 kilograms, right? Or sir, I weight this much pounds. If you're British, you would say pounds. If you are from Asia, you probably would say, I weight this much kilograms. So you must have some measurement unit, because units is what makes the quantity universal, the makes something that makes measurement universal. How? Let's see here. So the very first measurement units were those used in barter trade to quantify the amounts being exchanged and to establish clear rules about the relative values to different commodities. Without units, I think the trade wouldn't be much fair, because uh, it would be an estimation, right? It would not be a, a complete fair trade, because it would be an estimation, and estimations are never fair, right? They are estimates. So that system was based on whatever was available at measuring unit, and because it was based on whatever available as a measurement unit, it didn't had that the the assurance of fair trade. So see, and also it was very localized. So for example, see here, for the purpose of measuring length, human torso was a convenient tool, right? And gave us the unit of the hand. Then the feet came up, 1 foot, 2 foot, 3 foot, and the cubic. So although the generally adequate uh, allies for barter trade systems were uh, available, but they were not accurate, right? They were imprecise. They do vary as they do from one person to next, right? If you say if I want to measure something on the arm's length, the length of my arm can be different from the length of your arm. It is not accurate. Even though you can say you can simply say that a human arm would fall into the category of this to this centimeters or this to this feet, but you cannot directly say that how much it is going to hold. It will have a range, but will it have a, a short value, or will it have a determined value? No, it will not. So it's fuzzy. So therefore, there has been a progressive movement towards the measurement unit that are defined much more accurately. So the first measurement unit which was uh, found or improved for the measurement, it was meter, the measurement of length or distance, right? And how did it got defined? So it is defined as 10 raised to minus 7 times the polar quadrant of the earth. And if you are aware of the for the measurement, if you are aware of the SI unit systems, there are different systems that define units for different commodities or quantities. There is a system called SI systems or SI unit, that that is something that calibrates that unit of length or any other quantity. So how did they define the length of a length of 1 meter? So there is a platinum bar made to the length of 1 meter, and it's been established at a standard of length in the early part of the 19th century, and that got superseded by a superior quality standard bar in 1889, when the manufacturer from a platinum iridium alloy got used instead of platinum bars. Because what happens, platinum, if you are aware of, there is a fair possibility of contraction and expansion in the platinum based on different weather situations. So it is not very much feasible to use it, right? So since that time, technology research has enabled further improvements to made in the standard usage for defining length. So first in 1960, a standard meter was redefined in terms of 1.65, and you can read the unit here, into 10 raised to 6 wavelengths of a radiation from krypton 86 in vacuum. After that, in 1983, again meter was redefined as the length of the path traveled by light in an interval of 1 by 299,792,458 seconds. And uh, if you measure the speed of light, you will find this value. We simply write it 3 into 10 raised to 8 kilometer per second. But where did it came from? Yeah, light didn't came from the travel. Light didn't came from speed of light didn't came from the measurement of meter, but actually meter came from the speed of light, or the path traveled by light in a second, right? And in a similar fashion, we have defined different quantities. You can say ampere, you can say candela, you can say any other quantity. You can say mass, weight, acceleration, right? Time, seconds, right? Anything. So the early establishment of standard for the measurement of physical quantities proceeded in several countries at broadly parallel times, and in consequence, several sets of units emerged from for measuring the same physical variables. For instance, length can be measured in yards, meters, or several other units. Apart from the major units of length, subdivision of standard units exist, such as feet, inches, centimeters, millimeters, or even we use um, some local units for measurement as well, right? Like arm's length. And if you're in astronomy or sky watching, you can even measure the distance with the use of your fingers, right? We measure angles with the use of the fingers. If you're astronomers, you would know that. So with fixed relationship between each fundamental unit, it is subdivision. And here we have the definition of standard units, how it got defined, right? Length has a meter, and as we discussed it, how did it got defined? The length of the path traveled by light in an interval of 1 by 299,792,458 seconds. So uh, light travels a meter in this much of a second. You can imagine how fast light is. How did the kilogram got defined? So the mass of the platinum iridium cylinder kept in a International Bureau of Weight and Measurements in Paris, it generalized the 1 kilogram. How did a second got defined? So it got defined from the radiation cycle of vaporized calcium, calcium 133. How did a Kelvin got defined? So the temperature difference between absolute zero and the triple point of the water, defined as 273.16 Kelvin. The Kelvin got defined. Based on Kelvin, we got other different um, temperature units like Kelvin, Fahrenheit. How did ampere got defined? So it is current flowing through two infinitely long parallel conductors of a negligible cross section placed 1 meter apart in vacuum, and processing and producing a force of 2 into 10 raised to minus 7 Newton per meter length of conductor. How did candela got defined? Candela is basically luminous intensity, and the terms or the physical quantities we are going to discuss in uh, this section, there are 7 in total. These are the only the completely natural physical quantities. The other quantities will always be based on either of the, these quantities. It could be multiplication, it could be a simple division, it could be something more complex than that. It could be a multiplication of two of them and division of one of them, or multiplication of two of them and division of two of them, right? It can come from anything. Like for an instance, if I want to define the velocity, how do we define the velocity, right? It is length divided by time. So that's why you say velocity is not a natural commodity or natural 100% physical quantity. It's based on 200% physical quantities: length and time. Same ways you can come towards different things. If you want to measure the force, Force, how do we define force? F is equals to m into a. Now you know m, right? You know m, mass is a physical quantity. A for an acceleration, how do you define the acceleration? For acceleration, you what do you need? You need uh, speed per time. Now you already know what is speed, length divided by time. So what will you do? You will divide it divide your quantity with time one more time. So what did we got? Length divided by time twice. That would be your acceleration. And when you multiply it with mass, what you would get? You would get force. Same ways you can get work done. Same ways you can get power. Same ways you will be able to find different commodities, right? And same ways we can define the cadela and mole as well. I'm not going to in details of that. You can see from the book. Here we are having different SI units which I've told you about earlier. For length we have meter, for mass we have kilogram. Here are the symbols. How do we define it? Electric current we have ampere, time we have seconds, temperature Kelvin, luminous intensity candela, matter we have mole. For those who work in chemistry, you would be more familiar with mole. Then we have supplementary fundamental units. Uh, Basically, if you don't understand that much complex, just understand it by angles. Plane angle and solid angle, there are two type of angles. Plane angles we have unit of radian, we represent it with rad, and solid angle we have steradian, we represent it with sr. Then we have derived units which I was discussing few seconds ago, few minutes ago. You have area, volume, velocity, acceleration, angular velocity, density, kinematic viscosity, electric capacitance, electric induction, resistivity, permeability, current density, everything. I'm not going to discuss about them in detail, but just so that you know, I'm going to show you over here. So here are different measurement things which we use: magnetic flux, flux density, field of strength, frequency, luminous flux, luminance, illumination, molar volume, molarity, molar energy, different units. So we are going to discuss or carry out the further discussion about measurement system application in the very next chapter. In the very next lecture. And I will be seeing you next time with this. Meanwhile, you can drop your feedbacks, or you can if you have any feedbacks, if you have any suggestions or any questions or queries, you can mention them in the comment section below. I will be answering them as soon as possible, and as many of them as possible. I will be seeing you next time. Till then, thank you very much for listening. See you next time. Goodbye for now.